Okay, so h of x, right. So I didn't write this correctly. Here, if the way I wrote it, if x was not equal to 0 or 1, then this would be 0, this would be 0, so the whole thing would be 1. But that's not the right PMF here. So I should have put, maybe here, 0 otherwise. So I needed a function and another indicator function. Let me just put h of x here, where h of x, maybe I'll switch colors so I can insert it. So this is now, I'll put it in front. H of x, and then I have an h of x here, wherever it is. Front again. H of x. And h of x, I'll just define it here. H of x is the indicator that x is in 0 or 1. So I could put it this way. I could put the indicator of the set 0, 1. Another way to use indicator functions. This is sort of two different ways of using indicators. This is sort of the standard way. You put the set down here, and then it's a function of x. But oftentimes we write it, put some condition in here, and it's 1 if that condition holds, and 0 otherwise. Okay, so we have this. This is our h of x. And right, and I said z of theta is just 1. And so now we have our eta 1, our eta 2, our s1, and our s2. They're all in the exponential. We have a z of theta is just 1, and h of x. And so that is precisely in this form. So Bernoulli is also a member of the exponential family. And remember, in this case, it's a PMF rather than a PDF. Or rather, it's a family of PMFs rather than a family of PDFs. So that's another example. And there's something. So this example also illustrates something interesting. We could have done this a different way. So there's not necessarily a unique way to write it in terms of these types of to write it as an exponential family. So let's write this a different way. We could have also taken this expression and this is also equal to 1 minus theta to the 1 minus indicator that x equals 1 times this h of x, because if x is not equal to 0 or 1, then the whole thing is 0. If x equals 1, then we get theta, and 1 minus 1 is 0, so this just is 1. And if x is 0, then this is 0 in the exponent, so this is 1. This is 0, and we get 1 minus theta. So we can do that, and then if we pull out a 1 minus theta from this, we get theta over 1 minus theta to the indicator that x equals 1 times our h of x here. And now, if we do the same trick, we do the x log type of trick, we get h of x, 1 minus theta, exp of log. So let's go ahead and move the indicator down. X times the indicator that x equals 1 times log theta over 1 minus theta. And now this, in this formulation, or at least in this way of writing it, we have eta of theta here is just this thing. It's log theta over 1 minus theta. S of x is this part, the indicator, x equals 1. Z of theta is 1 minus theta. Let me make more space for that. Z theta is 1 minus theta, and h of x is just the same, just this indicator. Oh, well, actually I should say 1 over 1 minus theta, because z is in the denominator. So this illustrates, because now we have, right before we had these two functions, and now we have just these one of each type, one eta function, one parameter function, and one sufficient statistic function. So there's not necessarily a unique way to write a given distribution or given family of distributions as an exponential family. Put it in the exponential family form. Now let me mention, talking about the form, we say that an exponential family is in natural form. So let me just say natural, or sometimes people say canonical form, if this eta function, actually the whole vector, like if it was eta 1, eta 2, eta 3, etc., is just the identity function. So eta of theta equals theta. So like, eta 1 of theta is, well, it would be theta 1 if, so in this case eta m would always be, remember m was the number of functions, eta 1, eta 2, up to eta m, and k was the dimension of the space that theta lived in. Right, let's go back up here and remind ourselves of this. And so we were saying that k is the space that theta lives in, and whereas m, there's m different eta functions. So here, in particular, this would be assuming m equals k. So eta 1 of theta equals, so these are just like the projections. Eta sub k of theta is theta k. Okay. So this is what's called an exponential family in natural or canonical form, and it turns out you can always put an exponential family in some natural form that satisfies this. And oftentimes it's much easier to work with. So it's natural mathematically speaking, but it's not necessarily natural from the perspective of what the parameters mean. So, for example, well, I won't give an example, but oftentimes this is easier to work with mathematically. Now let me mention, just to let you know, a huge number of examples of common distributions are exponential families, and I just rattle off a list here. So some families with densities include, well, we talked about exponential family. Also the normal, or Gaussian, is an exponential family. Beta, gamma, chi-squared, and many more. I won't list. Well, I guess there's infinitely many in some sense, but these are some common ones. Some distributions with PMFs that are exponential families. Bernoulli, binomial. We talked about the Bernoulli, also the binomial. The Poisson, the geometric. So tons of very familiar ones. Multinomial, and there's more. So these are just some examples to show you how very general this thing is. And just a final comment, just to mention a couple things which are nice about exponential families, is that from a statistical perspective, what's nice about them is that exponential families always have conjugate priors. And in some sense, in a certain sense, they're the only distributions with conjugate priors under certain conditions. And also they arise as the solutions to certain types of maximum entropy problems. So that's just a couple of the nice properties that exponential families have. Without going into detail on what exactly this means, I haven't defined conjugate priors yet, and I haven't made this precise, but just to sort of point you in the direction of what's nice about them. A couple things that are nice about them. Oh, and let me briefly, one last point here, to give you an example without proving it, of something that's not an exponential family. The classic example of a distribution which is not an exponential family is the uniform distribution on the interval from 0 to theta. So theta here is the parameter, and the problem is that the parameter is governing the support of this distribution. And the support, if you look at the expression, or the form for an exponential family, the support, that h of x function, can't depend on theta. It can only depend on x, and here it depends on theta. So this is an example of a distribution that's not an exponential family. And this sort of brings to mind, for me at least, the point. So an important point when you're working with exponential families is what you consider to be a parameter and what you consider to be fixed. So if I could, if instead we were talking about the uniform distribution on like 0 to a, where a was not a parameter, then this would be just sort of trivially an exponential family, because it would just, its PMF would just be like this constant, the indicator that x is in this interval 0 to a times 1 over a. So we could take this as our h of x, and this is our a to be our z of theta. And in that case, so then theta, there would be basically no parameter. So it would just be, this would be trivially an exponential family. And the distinction here is that we would not be considering a to be a parameter. We would just be thinking of it as some fixed constant. So it makes a difference when you're working with exponential families, what you consider to be parameters and what you consider to be fixed values.